Okay, let's start. Today we will learn how to calculate the likelihood ratio test. In the first question, we have x is follow geometric distribution P. That means x has a PF look like this. Go to P 1 minus P with power k minus 1 P. And the domain is k equal to 1, 2, 3, dot dot dot. Okay, and we want to derive a likelihood ratio test of the hypothesis testing. Look at this. Okay. So the problem 1, x is the geometry distribution P, and the hypothesis testing is like this. On the rule, hypothesis P is equal to 1 over 2, and on the alternative, P is equal to 1 over 3. And we want to find the likelihood ratio. So first step, we have to define the test. Find the test. Okay, so for the definition, the likelihood ratio test statistic is equal to this. The ratio of the likelihood. So the numerator is the likelihood of the, how about looking at this? The density of x condition on rule hypothesis. And the denominator is condition on alternate hypothesis. So we have to plug in the data. So it's equal to this. P equal to 1 over 2. Here is P equal to 1 over 3. Okay. And we have the density, so you look at this. 1 over 2 to the power k x minus 1. 1 over 2. 1 minus 1 over 3. K minus 1. 1 over 3. So we can see this can be equal to 4, 3, 1. Okay. So this is a decreasing function on x. It's a decrease function on x. So that means the rejection region of the likelihood ratio test is equivalent then to this, s greater than c. Okay. The reason is nice. Originally, the likelihood ratio test is this, smaller than c, and because this is in decreased function where x is increased. So if we want to find this is very small, then it's equivalent to find x is very big. So okay, so this is what we have to do. Okay, and then we have to find the truncation C alpha. So step 2, we have to find the C alpha. Okay. So first, we have to do is we want to find this, and we have to make sure this is smaller than alpha. Okay, and we have to find a critical point of C. And we say next value is C alpha. Okay, and then we can observe that this is decrease to needle as c go to infinity. Okay, yes. So near is this maximum C alpha such nice. And first one is greater than alpha. Then we let this say alpha be our reduced region. So the next step, and to define the test. So we can say we reject when x is greater than c alpha, and fail to reject, or we can say accept when x is smaller than c alpha. Okay, so that's our calculation test. Okay, and let's do question 2. In question 2, we have different data. Here we have n data. We have data with sample size n, and they are from double exponential distribution. So this is a distribution of the double exponential distribution. And in this case, they have a property. This, the absolute value of a double exponential distribution is follow the exponential distribution with parameter lambda. Okay, that is a useful property. Okay, and we have to test this hypothesis testing. So property 2, we have S1 to Sn. Now follow exponential, double exponential lambda. Okay, and we have to test the rule n. The rule hypothesis is lambda equal to lambda 0, and the alternative is lambda equal to lambda a. And we know that the lambda 1 is greater than lambda 0. Okay. Okay, so here they use 1. Okay, so I use 1 here. Okay. Okay, then we want to do the calculation test. So since the step 1, we have to find the test statistic. Okay, so this. Okay, I usually use this notation to denote S1 to Sn. Okay, so this means from the definition is the put of 1 to n, the density Si condition on rule hypothesis, and the denominator is condition on alternative hypothesis. This one, which one? Then we can plug in the value on the hypothesis testing. So this is lambda equal to lambda 0. And the denominator is lambda equal to lambda 1. Okay. Then next we have to plug in the density. So we know that alpha 1 to n, the density is 1 over 2, I think. Yes. Lambda 0 exponential of negative lambda 0 absolute value of Si. And it's the same as the one in the numerator. So let's look at this. And we can do some algebra, and you can know that this one is proportional to this. Lambda 1 minus lambda 0 and the summation of Si. Here you have to be careful. Is the test that this is a function of x. So we only care about the function of x. And we can get rid of the 1 only depend on the lambda, which is not depend on x. Okay. And these two are proportional. Okay. And because the lambda 1 is greater than lambda 0, I think that implies is an increased function on this value, summation of absolute value of Si. Okay, and that means the rejection region of the likelihood ratio test is equivalent to this, greater than this. Okay, this is the same result. Originally we have this, and this is an increased function of this. So that means if we want to find this is very small, it's equivalent to find this is very small. Okay. The step 2, we want to find C alpha. Okay. First, we know that Si is absolute value of Si is follow exponential lambda 0 under null hypothesis. So that means summation of Si absolute value is follow the gamma distribution with n 1 over lambda 0. Okay. So this is under rule. Okay. So now we know the distribution of this. So we will be able to find the truncation of C alpha. Okay. Because you know that this is the significant level. So, and this is also a CDF of the gamma n lambda 1 over lambda. So this is, you can look at this. This is the CDF of this. And we also know that the CDF of this is a increasing function on C. So this is go to 1 as C go to infinity. Okay. And we also know that this 0 is 0. So we will be able to find a truncation C alpha. And we can define the C alpha as the inverse function of this. Inverse of alpha. Okay, so this is how our C alpha. And you know, and this is a little bit different than the one in here, in question 1. Because the question 1 is it's a decreased rate variable. So we may not find an exact C alpha such that the significant level is alpha, but in this case we can, because this is a continuous rate variable. Okay, so this is our C alpha. In step 3, we always have to define the test. Define the test. Okay, so we can say we reject if the summation of Si, this is smaller than C alpha, and we accept if this is greater than C alpha. Okay, so this is our rejection region, so this is our test, our rule for test. Okay, so that's all.